A vertical circular motion controlled by only gravity. Here we are going to consider a second case, mass tied to the rod which is performing a vertical circular motion. So consider a bob tied to the rod and whirl along a vertical circles. Here, whatever the bob we have taken, that should be considered as a point mass, and the rod should be practically massless and rigid. So suppose this rod tied to the bob performing a vertical circular motion as shown in figure. So basic difference between the rod and the string is that the string need some tension at all the points including the uppermost position, and thus for the certain minimum speed at uppermost position is always given by VA is equal to square root of RG. But in the case of rod, as the rod is rigid, the condition is not necessary and we can get the uppermost position. The velocity of the rod becomes 0. So practically the speed is 0 at uppermost position in case of rod performing a vertical circular motion. Let us solve one application. In a case of rod, as a rod is rigid, performing vertical circular motion, show that V lowermost is equal to square root of 4Rg is equal to 2 square root of Rg. Here we have assumed that the rod to be very light to solve this problem. Also, we have assumed the dimension of a block negligible compared to this length of the rod. So, rod is attached to this block and they are performing a vertical circular motion, and we have to calculate the V lowermost value, which is equal to square root of 4Rg is equal to 2 square root of Rg. Now, since the rod is very rigid, so the minimum velocity required given to the mass at the bottom most point of a trajectory should be such that the mass just able to reach the topmost point of a vertical circular path. So we know that in the case of rod, when the rod is reached to the topmost position, the velocity at this point is 0. So this is the critical case of a body to move in a full vertical circle. So continuing the same situation, here we have taken the rod, block and earth. Rod, block and the earth as a system, we can apply a total mechanical energy conservation as no work is done by external agents such as hinge on this system. Also, we have neglected the air resistance, hinge friction and other field. We have only considered that this system is performing without any resistance or vertical circular motion. Let VA be the minimum velocity at the uppermost position A, and that is always 0 in case of rod. Let VB be the minimum velocity at point B. Now we know that when the point is moving from bottommost position to the uppermost position, its potential energy increases, and when the point is moving from point A to point B, its potential energy decreases. So we know that at the bottommost position, the potential energy level is 0, and at the A position, its potential energy is more. But the kinetic energy decreases, so it is called as a retarded path. And when it is coming from uppermost position to the downmost position is potential energy decreases and kinetic energy increases. So it is called as a accelerated part. Hence, corresponding decrease in a gravitational potential energy from A to B is converted into the kinetic energy. So we can write here gain in potential energy or decrease in the potential energy is equal to difference in a kinetic energy at point B and the A. Just substitute the values over here in this equation. Gain in potential energy we can calculate as a PE is equal to mg into 2r as the object is get lifted at a distance of 2r. Then substitute this in equation. We can get mg into 2r is equal to kinetic energy at point B, that is half m Vb square minus half m Va square. This is a kinetic energy at point A. We have taken the difference between the kinetic energy of a point B and A. Taking the common term out of the bracket, that is a half m, we can write 2 mgr is equal to half m Vb square minus Va square. We can cancel out the term m from both the sides and rearrange the equation. We can write the equation as Vb square minus Va square is equal to 4rg. Now we know that in case of rod, the uppermost position, the velocity is 0. So just substitute the Va square value as a 0. We can write here the 4 Vb square minus 0 is equal to 4rg. Then rearrange the term, we get Vb square is equal to 4rg. So we can write down the Vb is equal to square root of 4rg. Take the square root of 4, that is 2. So we can rearrange the term and we can write here Vb is equal to 2 square root of rg. This gives a required minimum velocity of a rod at lowest point to travel along a vertical circle. Also note that this velocity is independent of a mass of a block but depend upon the radius of a vertical circle or the length of the rod. Consider second case. In a case of rod, as the rod is rigid, performing vertical circular motion, show that V horizontal is equal to square root of 2rg. Here also we have considered that a light rod is attached to the point mass m and is performing a vertical circular motion. The velocity at the bottommost position is 4r, square root of 4rg. Here also the potential energy is 0. When it coming to the uppermost position, its velocity becomes 0 over there. We have to find out the velocity at the horizontal, and therefore we are going to use a law of conservation of energy, that is total energy at point A is equal to total energy at point C. Total energy is the summation of kinetic energy and the potential energy. So we write the equation kinetic energy at point A plus potential energy at point A is equal to kinetic energy at point C plus potential energy at point C. Kinetic energy by formula we can write down half m Va square. Va is the velocity at the point A plus 2 mgr, that is the potential energy at point A, as the point object is get lifted up to a distance 2r, is equal to kinetic energy at point C. It is given by half mvc square, where vc is the velocity at midpoint of this circular motion, plus potential energy at point C, that is the object is get lifted up to a just distance r. So it is can be written as mgr. So by substituting the value, we get the value as a half mva square plus 2 mgr is equal to half mvc square plus mgr. Here we have to substitute the value of va as a 0, and this term will get it as a 0 factor, and write down the rest term as it is. So Rearranging the term, we can write down here 2 mgr is equal to half m Vc square plus m. Considering the same equation, we get 2 mgr is equal to half m Vc square plus mgr. Just move this mgr term from right hand side to the left hand side and do the subtraction. We get the equation is half mvc square is equal to mgr. Here we just cancel out the common term m from both the side, and we get the equation as vc square is equal to 2gr, and hence the vc we get it as a square root of 2rg. As the point D is also uh, a midpoint, so we can write the equation as VC is equal to VD is equal to square root of 2RG. So this is a diagram of that rod attached to the bob and performing a vertical circular motion, and it is also denoted all the velocities. When the rod is at the uppermost position, the velocity is 0. When it is at the bottommost position, the velocity of the rod is always given by square root of 4rg, and when the rod is horizontal, the velocity of this bob is always given by square root of 2rg. Consider the third application. Show that for a rod performing a vertical circular motion, T lowermost minus T uppermost is equal to 6 mg. That is, we have to prove that the difference in tension at lowermost position and the uppermost position is equal to 6 mg. Here we have considered a vector diagram of the rod performing a vertical circular motion. We know that at the uppermost position, the velocity is always 0, and at the bottommost position, the velocity is given by square root of 4rg. Also, if you see the vectors at the uppermost position, the vector mg and vector ta both are directed towards the center and balances the centripetal force. Also, at the lowermost position b, weight vector mg is directed downward direction, and it is just opposite to that of the tension tb vector, which is directed towards the center and balances centripetal force. So from this point A, we can write the equation 1 as Ta is equal to m Va square upon r minus mg. Here this m Va square upon r is nothing but centripetal force. And from the point B, we can write down the equation as Tb minus mg is equal to mvb square upon r. Rearrange the equation. We can write Tb is equal to mvb square upon r plus mg. Mark it as equation 2. Subtract the equation 1 from 2. We can write Tb minus Ta is equal to mvb square upon r plus mg minus into the bracket mva square upon r minus mg, close the bracket. When you open this bracket, you can write mva square with a minus sign, and minus of minus mg become plus mg. So we get the equation as Tb minus Ta is equal to mvb square upon r plus mg minus mva square upon r plus mg. From this equation, we can take out the common term m upon r from mvb square upon r and mva square upon r, and we can write the equation as Tb minus Ta is equal to m upon r into the bracket Vb square minus Va square, close the bracket, plus 2mg. Now, we can substitute the value of Vb and Va from this vector diagram. The square root of 4rg is nothing but the 4rg, and the square of the 0 is 0. So just substitute the value of this VB square and the VA square in this equation. We can write the equation as TB minus TA is equal to M upon R into 4rg minus 0 plus 2mg. So rearrange the term, we can write here M upon R into 4rg plus 2mg. Here we can cancel out the term R from the numerator and denominator, and we can write the equation as TB minus TA is equal to 4mg plus 2mg. Add these factors. So we can write TB minus TA is equal to 6mg. That is the T lowermost minus T uppermost is equal to 6mg.